Statistical learning extends classical econometrics by placing greater emphasis on prediction, regularisation, and honest out-of-sample evaluation. The central question is not whether one tradition replaces the other. It is how modern predictive tools can complement careful modelling, estimation, identification, and diagnostic reasoning. We begin by separating prediction from causal and structural interpretation, because the objective determines how a model should be trained, evaluated, and ultimately used. Classical econometrics often begins with a researcher-specified model and treats its parameters as the main objects of interest. A regression slope may represent a marginal effect, an elasticity, or a risk exposure. We ask whether an estimator is consistent, efficient, and approximately normal, and whether a confidence interval or hypothesis test is valid under explicit assumptions. Interpretation and uncertainty are therefore central parts of the exercise. Statistical learning shifts attention toward the prediction function. Given a collection of inputs, how accurately can we predict an outcome for a new observation that was not used to fit the model? Coefficients may still matter, but they can become instruments for constructing a useful prediction rule rather than final scientific targets. That change in objective also changes how we judge fit, complexity, and success. Machine learning helps with several recurring tasks in applied economics. It can build variables out of messy records. It can predict events or continuous outcomes. It can estimate flexible nuisance functions that later feed a causal procedure. And it can surface empirical patterns that may guide new theory. These jobs are genuinely different. A model that forecasts well need not identify a causal effect, and a good measurement tool need not hand us an interpretable structural parameter. Consider a demand equation. If our purpose is to estimate a price elasticity, we need economic structure, an identification strategy, and valid uncertainty statements. If our purpose is to forecast next month's sales, a flexible predictor may be judged mainly by future forecast loss. The same data can support both questions, but the assumptions, validation design, and claims must be matched to the question actually being asked. In-sample fit is an unreliable judge of predictive performance. Adding regressors can only reduce the residual sum of squares on the observations used for estimation. Yet, extra flexibility may fit accidental noise that will not recur. A model can therefore look excellent on its training sample and perform badly on new data. This gap between fitting and generalization is the practical meaning of overfitting. The bias-variance trade-off helps organize this problem. A very simple model may systematically miss real curvature or interactions, creating high bias, but its estimate changes relatively little across samples. A highly flexible model can follow the true pattern more closely, yet it may respond strongly to small sample fluctuations, creating high variance. Good prediction balances these two sources of error rather than minimizing either one alone. This perspective links machine learning to familiar econometric problems. Multicollinearity makes ordinary least squares coefficients unstable. A large vector autoregression can consume degrees of freedom. A non-parametric estimate can become too rough when its bandwidth is too small. In every case, the model is too flexible relative to the available information. Regularisation offers a systematic way to trade a little bias for a potentially large reduction in variance. Prediction and inference should not be treated as enemies. Many projects need both. We may want a forecast that is accurate enough for planning and a small set of effects that can be interpreted. Regularized linear models occupy a useful middle ground because they retain a recognizable regression form while stabilizing a large collection of coefficients. Their predictive success, however, does not automatically validate ordinary confidence intervals after selection. Honest evaluation begins by separating model fitting from final assessment. The training set is used to estimate candidate models. A test set is held aside and used only after important choices have been made. If the test results repeatedly influence feature design or tuning, that set has quietly become part of training. A fresh test period is then needed to obtain an honest estimate of performance on unseen observations. Tuning parameters require a validation mechanism. Examples include the strength of a coefficient penalty, the depth of a tree, or the minimum number of observations allowed in a leaf. A validation sample can compare candidate settings without touching the final test sample. When data are scarce, reserving one fixed validation sample can be wasteful, which motivates cross-validation as a more efficient form of repeated holdout evaluation. In K-fold cross-validation, we divide the sample into K parts. Each part takes a turn as the validation fold, while the other parts are used for fitting. We average the resulting validation losses and choose the tuning value with the smallest average. This process estimates predictive performance more honestly than training error, but it still has sampling variability. Tiny differences between nearby tuning values should not be overinterpreted. Time series demand a different validation design because the observations have an order and may be dependent. Randomly shuffling future observations into a training fold creates information that would not have existed at the historical forecast date. A realistic procedure trains on the past and evaluates on the next period. Rolling windows keep a fixed history length, while expanding windows retain all observations available up to each forecast origin. Temporal validation also has to reproduce data preparation. Scaling constants, missing value rules, transformations, and feature selection must be estimated inside each training window and then applied to its validation block. If a full sample, mean or standard deviation is used before splitting, future information leaks backward. Leakage can make a weak model appear impressive, so the entire pipeline, not only the final regression, must respect time. The chosen loss function should reflect the purpose of prediction. Root mean squared error gives relatively large weight to large mistakes. Mean absolute error is less sensitive to extreme observations. Classification problems may require probability scores rather than a simple accuracy rate. No single measure is universally best, and comparing many measures after seeing the results can create another form of selection bias unless priorities were specified in advance. Earlier chapters already contain the foundations of this workflow. Regression diagnostics teach us to inspect assumptions rather than trust a fitted coefficient table. Time series models teach us to respect dependence, stationarity, and forecast origins. Non-parametric methods teach us that smoothing parameters control effective complexity. Machine learning extends these lessons to larger candidate model classes and makes out of sample performance a central design criterion. The responsible workflow is therefore clear. State whether the target is explanation, causal inference, or prediction. Build every candidate model using information genuinely available at the forecast date. Tune complexity within the training data, preserve a final evaluation sample, and compare against simple benchmarks. Then, describe what the evidence supports and what it does not. The next lesson develops regularized regression as one concrete implementation of these principles. In the last lesson, I promised a concrete way to trade a little bias for a lot of stability. Regularized regression is that method. It keeps the familiar regression idea, but changes the fitting criterion. Ordinary least squares picks the coefficients that minimize the sum of squared residuals. When the predictors are many or highly correlated, that unrestricted solution can be unstable. So we add a penalty on coefficient complexity accepting some bias in return for lower variance and often better predictions on new data. Suppose the outcome at time t equals the inner product of a predictor vector and a coefficient vector, plus an error. If the number of predictors is small and the design matrix has full rank, ordinary least squares is well defined. When the predictor count approaches the sample size, small data changes can produce large coefficient changes. When predictors outnumber observations, many coefficient vectors may fit the training data equally well. The general penalized criterion combines average squared prediction errors with lambda times a penalty on the coefficient vector. Lambda is a non-negative tuning parameter. When lambda is 0, we recover ordinary least squares. As lambda increases, the penalty has greater influence, and the fitted model becomes less flexible. The useful value of lambda is an empirical question that should be answered with validation data rather than training fit. Ridge regression uses the sum of squared coefficients as its penalty. Its solution shrinks every slope towards 0 and remains unique even when predictors outnumber observations, provided the penalty is positive. Ridge is particularly helpful when several predictors carry similar information. Instead of assigning a large positive coefficient to one and a large negative coefficient to another, it distributes the signal more smoothly and stabilizes the combined prediction. Ridge generally does not set coefficients exactly to 0. That property can be an advantage when the signal is dense, meaning that many predictors each contribute a small amount. It can be a disadvantage when a compact selected model is important. The method should therefore be described as shrinkage, not automatic variable selection. A small ridge coefficient is still part of the prediction rule. The lasso uses the sum of absolute coefficient values as its penalty. The corner shape of this penalty allows some estimated slopes to become exactly 0. Lasso therefore combines shrinkage with variable selection. As lambda rises, the active model usually becomes smaller. This sparsity is attractive when we believe that only a limited subset of many candidate predictors carries useful incremental information. In a simple orthogonal setting, the lasso follows a soft threshold rule. If an unregularized signal is smaller in absolute value than the threshold, its estimate becomes 0. If it exceeds the threshold, the estimate keeps its sign, but is pulled towards 0 by the threshold amount. This example explains both the selection benefit and the shrinkage bias that lasso can impose on genuinely large coefficients. Correlated predictors complicate variable selection. Lasso may choose one member of a highly correlated group and discard the others, and a small change in the sample may change which member is selected. Ridge tends to share weight across the group. Neither behavior is automatically correct. Selection stability, predictive loss, and the substantive meaning of the variables should all be examined before giving a selected coefficient an economic interpretation. Smoothly clipped absolute deviation, or SCAD, is a folded concave penalty designed to encourage sparsity near 0 while reducing shrinkage for large signals. Near 0, it behaves much like lasso. In an intermediate range, it gradually relaxes the penalty, and above a sufficiently large threshold, it leaves the coefficient nearly unchanged. The motivation is to select weak variables without heavily biasing strong effects. Under suitable regularity conditions, SCAD can possess an oracle property. Informally, it may identify the true non-zero set and estimate those active coefficients as efficiently as if that set were known in advance. This is an asymptotic statement, not a guarantee for every sample. It depends on signal strength, dimensional growth, dependence and tuning, and it does not remove the need for validation or sensitivity analysis. Unlike ridge and lasso, the SCAD objective is non-convex. Numerical optimization is therefore more delicate and may depend on starting values or algorithmic details. A reported solution should be checked for convergence and stability. The possible reduction in bias comes with this computational cost. In applications where prediction alone is the goal, a stable convex method can remain preferable even if a non-convex method has appealing theory. Predictors should usually be standardized before penalized fitting, because the penalty acts on coefficient magnitude. Without scaling, a variable measured in thousands can receive a numerically small coefficient, and therefore a different effective penalty from a variable measured in fractions. Standardization places predictors on comparable scales. The intercept is normally left unpenalized, and all scaling constants must be estimated using the training data only. Cross-validation chooses lambda by comparing genuine validation errors across a grid. Many software tools report both the error minimizing value and a more strongly regularized value, whose error is within one estimated standard error of the minimum. The latter often produces a simpler model with similar predictive performance. For time series, folds must be contiguous or rolling, so that future observations never help predict the past. The R package, a GLMnet, fits the full ridge and lasso coefficient paths very efficiently. A practical workflow follows a simple sequence. We build a numeric design matrix, fit the candidate penalties, and let cross-validation pick lambda. Then, we read off the coefficients at that value and predict the held-out observations. One caution. The package standardizes predictors by default and rescales the coefficients afterward, so record that behavior, because manual pre-processing and automatic standardization can otherwise be applied twice. The R package NCV reg gives us SCAD and other non-convex penalties. The workflow looks similar, but here we check convergence carefully and use time-respecting folds when the data are sequential. Remember that software convenience does not settle the methodology. A credible forecast depends on the choices we make. We must define the response clearly, date every feature, decide how to transform the data, and set the penalty grid, and keep the final evaluation period fixed. The book's macroeconomic example forecasts monthly industrial production growth from its own lags and lags of inflation, unemployment changes, and the federal funds rate. The lasso retains 17 of 52 candidate coefficients, including the intercept, and obtains a test root mean squared error of about 1.07. In that sample, it improves on the naive mean forecast at about 1.45 and ridge at about 1.33. The companion SCAD example retains 16 of the same 52 candidates and produces a test root mean squared error of about 1.09. Its selected set is similar to the lasso set, but its error is slightly higher in this realization. That comparison is useful precisely because it resists a simple winner story. A theoretically attractive penalty need not dominate in every finite sample. Regularisation can also organise high-dimensional lag structures in autoregressions and vector autoregressions, or forecast volatility from many lagged measures. Yet, selected predictors are not automatically causal, and conventional post-selection standard errors are generally invalid. Treat ridge, lasso, and SCAD first as disciplined prediction tools. If inference is required, use methods designed for post-selection or high-dimensional inference and state their additional assumptions. Regularized regression controls complexity while keeping a linear prediction function. A regression tree takes a different route. It divides the predictor space into regions and assigns a constant prediction within each region. This simple construction can represent non-linear relationships, thresholds, and interactions without asking the researcher to write every transformation in advance. The price is a discontinuous prediction surface and potentially high sampling variability. Imagine forecasting household expenditure from income and family size. A tree might first split households at an income threshold. Within the lower income group, it might split again by family size, while the higher income group receives a different split. The prediction in each final group is the average expenditure among training observations in that group. One predictor's role can therefore depend naturally on another predictor's value. Formally, the tree partitions the predictor space into non-overlapping terminal regions. For any new input, we locate the region containing it and report the mean outcome of training observations in that region. The fitted conditional mean is a step function. This local averaging connects trees to non-parametric regression, but the data determine both which variables define the regions and where their boundaries are placed. The method, called classification and regression trees, or CART, builds this partition through recursive binary splitting. Starting at the root, it looks at every eligible predictor and every candidate threshold. Each candidate splits the data into a left group and a right group. For a continuous outcome, CART picks the split that most reduces the within-group residual sum of squares, which is the same as making the two child nodes as pure as possible. The process repeats separately inside each child node. Because later splits can differ across branches, the tree automatically represents interactions. A threshold on inflation may matter only when unemployment is already high, for example. The algorithm is greedy. It chooses the best split available at the current step and does not revisit earlier choices to find a globally optimal partition. That limitation is important for understanding tree instability. Growth stops when a rule is reached, such as a minimum number of observations in a node, a maximum depth, or an insufficient improvement in fit. A deeply grown tree usually fits the training sample closely. Tiny leaves can reproduce isolated outcomes, but their averages are estimated from little information. Training error, therefore, keeps falling even when future prediction begins to deteriorate. Pruning controls this complexity after a large tree has been grown. Cost complexity pruning balances residual sum of squares against a penalty proportional to the number of terminal leaves. A small penalty favors a large detailed tree. A large penalty removes branches and yields a shallower model. Cross-validation chooses among the nested, pruned trees, using held-out prediction error rather than visual preference. The bias-variance trade-off is especially visible in trees. A shallow tree may miss smooth curvature and have substantial bias, but its broad regions are relatively stable. A deep tree can represent fine features and lower training bias, but its selected thresholds may change sharply when a few observations change. The preferred depth depends on predictive evidence, not on a universal rule that deeper or simpler is always better. A tree diagram is appealing because it exposes the sequence of decisions. Internal nodes display variables and thresholds. Branches show the resulting conditions, and leaves show predictions. Yet, visual clarity is not the same as causal interpretation. A split indicates that a variable helped prediction within this sample and feature set. It does not show that changing the variable would cause the outcome to change. The partition view reveals another limitation. Predictions are constant within a leaf and jump at its boundary. Two nearly identical observations can receive different predictions if they lie on opposite sides of a threshold. Conversely, two quite different observations can receive the same prediction inside a broad leaf. This roughness may be acceptable for prediction, but it should be remembered when the true relationship is expected to be smooth. Trees handle nonlinearities without polynomial engineering and can discover conditional thresholds that a simple additive regression misses. They also accommodate continuous and categorical predictors, with relatively little preparation, though exact handling depends on the software. Missing values, rare categories, and high cardinality factors still require attention. A model that accepts raw columns is not free from data quality or measurement problems. Economic interpretation can sometimes benefit from the hierarchy. An early split suggests a variable is useful across a large portion of the sample, while a later split refines a narrower subgroup. However, correlated predictors can substitute for one another, so the chosen hierarchy may not be stable. Refit the tree across resamples or nearby time periods before treating a particular threshold as a robust empirical regularity. Time series applications require the same temporal discipline as other forecasting methods. Lagged predictors must be dated so that every value was observable at the forecast origin. Tree depth and node size should be tuned on rolling or blocked validation periods. A random split can reveal future regimes during training and exaggerate performance, especially when the series contains persistence, structural breaks, or changing volatility. Extrapolation is another concern. A regression tree predicts with observed leaf averages and does not extend a linear trend beyond the range of the training data. If a new predictor value lies far outside that range, it still falls into an outer leaf and receives that leaf's historical mean. This can be safer than extreme linear extrapolation, but it can also miss a genuine continuing trend. The method is called adaptive non-parametric regression because it forms data-driven bins. Histogram regression uses fixed bins, while kernel regression uses neighborhoods controlled by a bandwidth. A tree chooses rectangular regions through sequential splits. The effective smoothing is governed by depth, minimum node size, and pruning. As with bandwidth selection, these controls determine how much local detail is retained and how much random noise is averaged away. A sensible diagnostic compares training and validation loss across tree sizes. A large gap with excellent training fit and poor validation fit signals overfitting. Inspect leaf counts to ensure predictions are supported by enough observations. Compare with a linear model and a simple mean benchmark. Also examine performance across calm and unusual periods, because an attractive overall average can conceal weak behavior where decisions are most difficult. Single trees are valuable for explanation and exploratory structure, but their high variance often limits predictive accuracy. Small changes in data can alter an early split and reorganize every branch beneath it. Ensemble methods address this weakness by averaging many deliberately varied trees. The next lesson develops bagging and random forests, where the goal is to retain flexible interactions while replacing one fragile partition with a more stable collective prediction. A random forest is an ensemble of regression trees designed to reduce the instability of a single tree. The starting idea is averaging. If several predictors make imperfect errors that are not perfectly correlated, their average can have lower variance than any one predictor. Trees are especially suitable base learners because they are flexible and unstable, so changing the data can create useful diversity across the ensemble. Bagging, short for bootstrap aggregation, creates that diversity by repeatedly sampling the training observations with replacement. A full tree is fitted to each bootstrap sample, and the final regression prediction is the average across trees. Averaging leaves systematic bias largely unchanged, but can reduce variance. The gain is greatest when individual trees are noisy and their errors are not too strongly correlated. Ordinary bagging can still produce highly correlated trees when one dominant predictor is chosen near the top of almost every tree. Random forests add another layer of randomness. At each candidate split, the algorithm considers only a randomly selected subset of predictors. Strong variables remain available often, but not always. This gives other variables opportunities to shape different trees and lowers correlation across their prediction errors. The forest prediction is the average of all tree predictions. Adding trees usually stabilizes that average rather than causing classical overfitting through model size. After enough trees, simulation noise becomes small and additional trees bring little change. The number of trees is therefore mainly a computational and stability choice. Other controls, including variables considered per split and minimum node size, more directly determine the forest's bias and variance. The parameter, often called MM_try, controls how many candidate predictors are examined at each split. A large value makes trees stronger individually, but more similar to one another. A small value increases diversity, but may prevent useful variables from appearing often enough. Minimum node size controls local detail. Small leaves permit complex patterns and higher variance, while larger leaves impose more smoothing. Each bootstrap tree leaves out some training observations. These omitted cases are called out-of-bag observations. For each observation, we can average predictions from trees that did not use it during fitting. Comparing those predictions with the observed outcome yields an out-of-bag error estimate. This is a valuable internal validation measure, although time-ordered data may still require rolling evaluation because ordinary bootstrap sampling ignores temporal structure. Permutation variable importance measures how much predictive performance deteriorates when one predictor is randomly rearranged in out-of-bag data. A large deterioration suggests that the fitted forest relied strongly on that variable. Importance is conditional on the available feature set and their dependence. Correlated predictors can share or substitute importance, and a predictive variable need not be a causal driver. Partial dependence describes the forest's average prediction as one selected predictor is varied, while the remaining predictors retain their observed values. It can reveal curvature or thresholds hidden inside hundreds of trees, yet the calculation may combine predictor values that rarely occur together. With strongly correlated economic variables, the curve can therefore evaluate unrealistic cases. It is a model summary, not an experiment. Random forests capture non-linearities and high-order interactions without asking the analyst to enumerate them. They are relatively insensitive to monotone rescaling and usually need less pre-processing than distance-based methods. They can also be robust predictive benchmarks when the true function has thresholds. However, they sacrifice the transparent equation and coefficient interpretation offered by a small regression or autoregressive model. Forests do not naturally extrapolate beyond observed outcomes in their terminal leaves. A forecast made under a new extreme regime is assembled from averages seen in the training sample. Structural breaks, unprecedented policy settings, or new market conditions can therefore challenge the model. Rolling estimation can update the forest, but no flexible algorithm can learn a regime that is absent from its historical data. For time series, standard random forest software often draws ordinary bootstrap samples from individual rows. That process is convenient, but it does not by itself create a realistic historical forecast experiment. Features must contain only lags and information available at the forecast origin. Hyperparameters should be selected with time-respecting validation, and the final comparison should use a later untouched period. Block resampling can sometimes preserve local dependence more faithfully than independent row sampling, but it changes the ensemble design and must be justified. Another practical approach is to use the forest as a supervised predictor on carefully lagged features while evaluating every decision with rolling origins. In either case, dependence does not disappear simply because the prediction algorithm is non-parametric. For random forests, the R package ranger provides a fast implementation. In a typical run, we give it a response formula and the training data, then set three things: the number of trees, how many candidate variables to try at each split, and the minimum node size. We also request prediction and permutation importance, set a random seed, and record the package versions. Once the forest is large enough, different seeds should give you almost the same aggregate results. The book's compact volatility example uses today's squared return, 5 additional lags of squared returns, and 5 lags of absolute returns to forecast next day squared return for SPYs. These 11 predictors are used by a forest with 500 trees. Its out-of-bag R squared is about 0.19, which means that most of the day-to-day volatility variation remains unexplained even inside the training design. In that compact example, the first and fifth lags of absolute returns and volatility receive high permutation importance. This should be read as evidence about the fitted predictor, not as a stable economic law. More importantly, the forest test root, mean squared error, is about 2.19, slightly worse than the naive mean benchmark at about 2.10. Flexibility did not guarantee improvement. That negative comparison is scientifically useful. A complex model can discover patterns and still fail to generalize. The proper response is not to search repeatedly through test results until one specification wins. It is to diagnose whether the signal is weak, features are poorly dated, tuning is inappropriate, or the evaluation period differs from training, and then test any revised design on genuinely new data. Forecast uncertainty is not supplied automatically by the forest's point prediction. Variation across individual trees mainly reflects algorithmic and bootstrap variation, not the full uncertainty of a future economic outcome. Prediction intervals require additional methods and calibration on held-out data. Their coverage can fail under changing volatility or dependence, so interval performance should be checked through time rather than assumed from a software option. Random forests are therefore best used as disciplined benchmarks alongside simpler models. Report out of bag diagnostics, but rely on a true out-of-sample experiment for the main claim. Examine importance and partial dependence cautiously. Quantify uncertainty across forecast periods, and document tuning. In the next lesson, classical and machine learning forecasts are placed in one rolling comparison to show how such evidence should be interpreted. This final lesson brings classical time series models and machine learning predictors into a common forecasting exercise. The purpose is not to crown a universal winner. It is to make every model face the same target: information set, forecast origins, and loss function. Only then can differences in out-of-sample error be attributed meaningfully to the modelling choices, rather than to an uneven evaluation design. The case study uses daily adjusted closing prices for SPY over a multi-year sample. Log returns are expressed in percent, and squared return is used as a simple daily volatility proxy. The target is next day squared return. This noisy proxy connects the exercise to conditional variance models, but it is not a direct observation of latent volatility and can contain considerable measurement variation. The sample is divided chronologically into an initial training period and a later evaluation period. At each forecast origin, a model is estimated using information available up to that date and produces a one-step-ahead prediction. An expanding window keeps all past observations, whereas a rolling window retains only a fixed recent history. The choice trades additional sample size against adaptation to structural change. Accuracy is summarized with root mean squared error, which takes the square root of the average squared forecast error. This loss emphasizes large misses, a relevant feature when volatility spikes matter. Mean absolute error can provide a complementary view that is less dominated by extremes. A fair comparison computes every model's loss over the same dates and handles missing forecasts consistently. The first classical benchmark is an auto-regression for squared return. An order, one version predicts tomorrow's squared return from a constant and today's squared return. Higher orders can include more lags, selected with an information criterion or validation procedure. The model is transparent and captures linear persistence, but it does not explicitly represent the conditional heteroskedasticity mechanism that motivates volatility models. The second benchmark is a generalized autoregressive conditional heteroskedasticity model of order 1-1, which we call GARCH 1-1. Tomorrow's variance is built from three pieces: a constant plus a coefficient on the most recent squared return plus a coefficient on the previous conditional variance. Positivity and persistence restrictions keep the process well behaved, and the fitted recursion produces tomorrow's variance forecast directly. The machine learning models use a richer feature vector. It includes lags of squared returns, lags of absolute returns, moving averages that summarize short and medium volatility, and possibly calendar indicators. Every feature must be constructed as it would have existed at the forecast origin. Even a one-day alignment error can place the target or future return inside the predictor matrix and create severe leakage. The lasso fits a linear forecast to these features while shrinking weak coefficients and setting some to 0. Its penalty is selected inside the training period using blocked or rolling validation. Predictor means and scales are also estimated inside each training window. The selected penalty is then fixed for the outer evaluation step so that test outcomes do not influence model complexity. The random forest uses the same dated feature vector, but allows non-linearities and interactions. Its principal controls include tree count, candidate variables per split, and minimum node size. Out-of-bag error can help screen settings, while rolling validation is safer for the final choice in a dependent series. Using identical features helps separate functional flexibility from differences in information. In the leakage-safe rolling comparison, the root mean squared errors are about 1.33 for the autoregression, 1.20 for GARCH, 1.27 for lasso, and 1.29 for the random forest. GARCH has the lowest error in this design. The lasso and forest remain close to the autoregressive benchmark, showing that greater flexibility does not automatically improve volatility forecasts. Those rankings are sample and design specific. They do not prove that random forests generally dominate volatility models. Indeed, the compact forest example in the previous lesson used a different sample and feature construction and performed slightly worse than a naive mean forecast. The contrast demonstrates why a result must always be attached to its precise target, period, feature set, tuning procedure, and evaluation protocol. The realized volatility plot reveals another important feature. Lasso forecasts are much smoother than squared returns. They track broad changes in the volatility level, but tend to underestimate sudden spikes. Shrinkage contributes to this smoothness, but the deeper reason is that extreme market movements contain a large unpredictable component. A forecast should not be condemned merely because it cannot anticipate every shock. Classical models retain major advantages. Autoregressive and GARCH parameters have recognizable interpretations, established diagnostics, and a direct connection to time series theory. Residual dependence, remaining conditional heteroskedasticity, and parameter stability can be tested. A machine learning predictor may reduce forecast loss, but it usually offers less transparent explanations and is not designed for structural or causal claims. Machine learning offers a different advantage. Regularized regression can include many correlated lags without unstable ordinary least squares estimates. Forests can capture thresholds and interactions that were not specified in advance. These methods are especially valuable as flexible comparison models. If they outperform a classical benchmark, the result may signal non-linear structure or omitted predictive information worth investigating further. Model comparison should include uncertainty, not only a ranking table. Forecast errors are dependent over time, so small differences in average loss may not be meaningful. Loss differential tests, block-based uncertainty estimates, and performance across sub-periods can reveal whether an apparent gain is stable. Results should also be checked with more than one reasonable loss function when the forecasting objective permits. Changing regimes deserve explicit attention. A model trained in a calm period may fail during a crisis, while a short rolling window may adapt faster but estimate parameters less precisely. Plot cumulative loss and errors through time rather than reporting only one average. If one model wins because of a handful of extreme dates, say so. That pattern may be substantively important, but it is different from broad dominance. Data revisions and availability dates matter in macroeconomic applications. A series downloaded today may contain revised historical values that were not known at the original forecast date. A credible real-time study uses vintages when possible. Financial prices are revised less often, but corporate actions, trading calendars, and time zone alignment can still create mistakes. Prediction accuracy cannot repair a contaminated information set. For reproducibility, I ask you to write a few things down carefully. First, where the data came from and when you downloaded it. Second, every transformation and feature definition you used. Third, the window scheme, the random seeds, the package versions, and the tuning grids. Keep the final evaluation data untouched until your analysis plan is stable, and let your public code rebuild every forecast from the raw inputs when licensing permits. Good documentation is what lets a reader tell a real finding from an accident of hidden pre-processing. So where does this leave us? The two traditions are complements, not rivals. Classical econometrics gives us structure, interpretation, diagnostics, and disciplined assumptions. Machine learning gives us regularization, flexible function classes, and a relentless focus on unseen data. The strongest empirical work uses both. Start with simple benchmarks, validate every choice in the correct time order, and add complexity only when the evidence shows it buys you a reliable gain. This chapter has introduced only selected tools. Boosting, neural networks, causal machine learning, and modern high-dimensional inference require separate treatment. The principles developed here still carry forward. Define the target, prevent leakage, tune within training data, evaluate on genuinely new observations, and distinguish prediction from causation. Those habits matter more than the name of any algorithm and form a durable econometric workflow.